This is SpaceTime, Series 22, Episode 37. Coming up on SpaceTime, the first possible detection of a black hole merger with a neutron star, the Milky Way's massive collision which triggered a huge starburst, and a strange, different type of supernovae in the early universe. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers may have just detected their first case of a black hole devouring a neutron star. If confirmed, the long-predicted but never-before-seen event on April the 26th will be making scientific history. The candidate event is one of several potential new detections of gravitational waves achieved during the opening days of the third observational run of the LIGO and Virgo detectors. Other candidate signals include a possible second merger between two neutron stars just a day earlier on April the 25th, and three potential additional mergers between binary black hole systems on April the 8th, 12th, and 21st. While black hole mergers cannot be seen with conventional telescopes, dozens of observatories on Earth and in space are carefully searching the skies for electromagnetic or astroparticle counterparts for both the binary neutron star merger and the possible collision of a black hole with a neutron star. However, so far no identification of an electromagnetic transient signal nor a host galaxy has been made of either candidate. Gravitational waves for the binary neutron star event, designated as S22E37, arrived on Earth at 8:18 Greenwich Mean Time on April the 25th. However, only the LIGO Livingston Observatory and the Virgo detector were taking data at the time, and only Livingston actually registered the event, which was too faint for Virgo to detect with any high statistical significance. Because of these reasons, the sky localization for S190425Z is less precise than what it was for the GW170817 signal, which was the first neutron star merger ever detected by gravitational waves and which was observed using all three instruments. It was also much closer and therefore louder. The initial LIGO Virgo observations have constrained the position of S190425Z to two patches together covering a huge part, roughly 25% of the sky. Automated analysis of the candidate signal ranked it to be a neutron star merger with more than 99% probability. Further inspection by LIGO Virgo scientists have now improved the sky localization and estimated the signal to be at a distance of between 370 and 640 million light-years from Earth. Now, by comparison, that GW170817 signal, the first ever binary neutron star merger, was just 130 million light-years away. But the signal everyone's talking about now is the possible black hole neutron star merger which occurred the next day. It's being catalogued as S190426C and was observed by both LIGO detectors and the Virgo instrument at 15:22 Greenwich Mean Time on April the 26th. LIGO Virgo analysis places the signal at a relatively remote distance of somewhere between 900 million and 1.6 billion light-years away. And it's providing a sky map for astronomers to search for expected electromagnetic and astroparticle counterparts over an area of the sky covering about 1,100 square degrees. That's roughly 3% of the total sky. Following public LIGO Virgo alerts regarding S190425Z and 190426C, more than 150 follow-up reports from both electromagnetic and astroparticle observatories, both on the ground and in space, have been issued. Now, as we mentioned earlier, none of them have as yet identified a counterpart to the gravitational wave candidates, but further observations are ongoing. Meanwhile, LIGO and Virgo scientists are closely analysing the gravitational wave data to better understand the statistical significance of both events and the astrophysical properties of their respective sources. When two black holes collide, they warp the fabric of space-time, producing gravitational waves. But that really is all. There is no visible counterpart. But when two neutron stars collide, they not only send out gravitational waves, but also light. That means telescopes sensitive to light waves across the electromagnetic spectrum can witness these fiery impacts together with the LIGO and Virgo observatories. A good example of this was the GW170817 event, which occurred back in August 2017 and was initially spotted by LIGO and Virgo as a neutron star merger in gravitational waves, and then in the days and months that followed by about 70 telescopes on the ground and in space, which witnessed the explosive aftermath in light waves, including everything from gamma rays through to optical and even down into the radio wave spectrum. LIGO is the Laser Interferometer Gravitational Wave Observatory. It comprises two identical facilities, one in Livingston, Louisiana, the other in Hanford, Washington State. Each LIGO observatory operates by firing highly precise lasers into a beam splitter, which then shoots the beams along two perpendicular 4-kilometre-long tubes equipped with mirrors at the far ends. The reflected laser light is then sent back to the detector, where eventually it should theoretically recombine. Now, as a gravitational wave generated by something like moving mass or merging black holes passes through the cosmos, it causes the very fabric of space-time to stretch and compress ever so slightly by just a fraction the diameter of a proton. And when one of these gravitational waves passes through the LIGO detector, the local space-time, including the two beamlines' reflected lasers, are stretched and compressed ever so slightly, leaving them out of phase. And that's the signature of the gravitational wave event. Using multiple gravitational wave detectors allows scientists to determine the direction of the wave. The addition of a third detector called Virgo, located near Pisa in northern Italy, has further improved detection. A fourth observatory, Japan's Kamioka gravitational wave detector, the first to be built underground, is expected to come online later this year. And a fifth gravitational wave detector, originally offered to Australia but rejected by the then Gillard Labor government, is now being built in India. These latest gravitational wave detections follow a major upgrade in the sensitivity of both the Virgo and LIGO detectors, which were already the most sensitive instruments on Earth. Professor Susan Scott from the Australian National University says these latest detections are just the beginning. With the larger volumes of the universe being probed by the improved technology in this third observation run, scientists are now witnessing more rare and extreme events. Instruments called quantum squeezers, which were designed by the Australian National University, were installed on the LIGO detectors to dampen the quantum noise which can drown out weak gravitational signals. The new squeezers are allowing the LIGO detectors to see much further into the universe and detect many more gravitational wave signals. Scott says astronomers are also using the ANU's Sky Mapper telescope to search for the electromagnetic counterparts to the neutron star mergers, scanning a massive region of the southern sky for potential signatures from the event.
The first month of the third observing run of LIGO and Virgo has been incredible. We've had 3 binary black hole system collisions. But as you alluded to, we've also had 2 incredibly exciting other events. The first one of which was our second ever binary neutron star collision. And this came in on Anzac Day, and we were incredibly excited by that. And the fifth one is one that came in the day after, and that's a very intriguing event that we're still analysing. It has the possibility of being an entirely new form of event compared with the ones that we've already had, in that it could possibly be a black hole neutron star collision, so a black hole swallowing a neutron star. But we're still a long way from calling that. We need to do a lot more statistical analysis of what was actually a very weak signal before we can really decide what it was.
Now, with the neutron star merger, the exciting thing there, of course, is we should be able to see a counterpart to that in the electromagnetic spectrum. How are those observations going?
Well, it became very difficult because at the time of the observation, only LIGO Livingston and Virgo were online. So Hanford was down, as it turned out, for quite a brief period of time, but unfortunately missed it. And because of the way that we determine a direction for the signal by triangulation between the time of receipt of signal in the various detectors, the more detectors we have, the smaller the area of sky we can actually send forth to the astronomers to look for a counterpart. So unfortunately, we had like a quarter of the sky for that detection to send out in our alert, 10,000 square degrees, which compared with our first detection of about 28, you can see it was a lot bigger portion of sky. And in that huge portion of sky, I think there are something like 45,000 potential host galaxies to to scan through. So, no, we haven't yet found the counterpart. I mean, on the first night, the ANU Sky Mapper telescope imaged two of the most likely possible sources, which were located close to the equator. But in our subsequent analysis, we found that they were actually new supernovae. So we didn't get the source, and at this stage, it's perhaps not likely that we are going to actually locate the counterpart for this detection.
This is all very exciting because with all these potential mergers coming in, it sort of follows on from exactly what the predictions initially were for LIGO once it got up and running and became more sensitive as it now is in its third reincarnation.
That's right. We'd predicted that with the upgrades that we implemented on the LIGO detectors in the year that we were down, that we might be able to have about one binary black hole collision per week detection, and also about one binary neutron star collision per month. And so far, after 1 month, those predictions are exactly spot on. We are seeing that kind of regularity in our detection.
With the binary neutron star mergers, what should we be seeing? I mean, with the black hole, we won't see anything because they're black holes. But with the binary neutron star mergers, assuming the resultant mass is great enough to become a black hole, what should we be seeing? Is there a sudden flash of light and then all of a sudden it goes dead?
Yes, what we see is, firstly, the two neutron stars are getting closer and closer, and then when they collide, they create in the collision a massive fireball, a kilonova, and this fireball is emitting light, and later on it will be emitting radio waves. But if we can latch on to the source very quickly after they've collided, we can gain a great deal of insight from this fireball as to what happens during a neutron star collision, how heavy elements are being produced in the universe through these collisions, and also perhaps an insight into the true nature of this very, very dense material which forms the neutron stars. And at this stage, we don't have a lot of information about that, but by studying these kilonova and these collisions, we hope to be able to get a much better handle on the properties of this very dense material.
Neutronium. I'm assuming a neutron star black hole merger would be very similar, but maybe with less light in the kilonova phase? Or would there be a kilonova, or would it simply be a bloop and it's gone?
We, through simulations, see this system as being largely spherical in orbit, and basically the neutron star will be orbiting closer and closer, and as it gets closer, parts of it will be ripped off from the black hole, and it will become very kind of messy in these inner orbits, and that should emit electromagnetic signals. We don't expect that will be as strong perhaps as the kilonova that we're getting through the neutron star collisions, but it will be an emitter of these types of electromagnetic signals, and if we get such a system close enough, we should be able to find a counterpart and observe the exact nature of that collision.
And that will also tell you what neutronium is, exactly what's going on inside a neutron star, maybe even its structure.
That's right, yes. As we see it progressively being torn apart leading up to the collision, then that will give us a much greater insight into the nature of that material which forms these very dense neutron stars.
One can even speculate we may see solitary quarks for the first time.
Well, we're still speculating here because this is quite some time off, but we are hoping to get a golden such event in this observing run, one that we can really latch onto and find a counterpart and observe it for the first time.
That's Professor Susan Scott from the Australian National University. And this is SpaceTime. I'm Stuart Gary. Astronomers have identified a truly massive collision that occurred between our Milky Way galaxy and a neighbouring satellite galaxy that triggered a sudden burst of new star formation, which increased the number of stars in our galactic disk by more than 50%. Evidence for the huge starburst event, reported in the journals Nature and Astronomy and Astrophysics, came through new observations from the European Space Agency's Gaia spacecraft. Gaia has been measuring the precise distances, compositions and magnitudes of billions of stars in the Milky Way, including more than 3 million nearby stars in the galactic disk. The authors then compared the Gaia data with cosmological models predicting the distribution of different stars across the galaxy. The study shows that since its creation some 12 billion years ago, new star formation in the Milky Way was gradually slowing down in the main disk as the available molecular gas to create new stars was slowly being used up over the first, say, 4 or 5 billion years of galactic evolution. Then, all of a sudden, something triggered a massive burst of new star formation, what's known as Starburst. The Gaia data suggests a small satellite galaxy rich in gas must have collided with the Milky Way, providing the fresh material needed to spark a massive new round of starburst. The study's lead author, Roger Moore from the University of Barcelona, says the timescale for the star formation burst, together with the great amount of stellar mass involved in the process, thousands of millions of solar masses, suggests the disk of our galaxy didn't have a steady and paused evolution. He says instead it received a sudden external perturbation which began about 5 billion years ago. Now, all this data fits in nicely with cosmological models, which suggest that galaxies grow through the merger of smaller galaxies into larger ones. And it's a process we can see occurring right now, with the Sagittarius dwarf galaxy being cannibalized by the Milky Way today. And it's not just what's happening on the other side of the Milky Way. On our side, not far from where we are, we can see the Milky Way is also gravitationally streaming gas and stars off two other dwarf galaxies, large and small Magellanic Clouds. And of course it's an ongoing process. In about 3.7 billion years' time, the Milky Way itself will be cannibalized when it collides with the much larger and more massive Andromeda galaxy, M31. Stand by for the fireworks. I'm Stuart Gary. This is SpaceTime. A new study suggests that instead of exploding out evenly in all directions as originally thought, supernovae generated by the death of the universe's first stars may well have exploded in elongated jets. Hundreds of millions of years after the Big Bang, some 13.8 billion years ago, the very first stars flared into the universe as massively bright accumulations of hydrogen and helium gas created in the Big Bang itself. These stars were very different to the stars we see in the universe around us today. They were all huge, tens to hundreds of times larger than our Sun, and they were much brighter and hotter, all of them huge blue giants. Within the cores of these first stars, extreme thermonuclear reactions forged the first heavy elements in the universe, elements such as carbon, iron, and zinc. These first stars were likely immense, short-lived fireballs. Even today, blue stars are considered the James Deans of the astronomical world, living fast and dying young. That's because they have so much heat, they burn through their nuclear fuel supplies very quickly. And these very first immense stars would have had extremely short lifespans, possibly living only for a few million years. But scientists have always assumed that when they died, they exploded in very spectacular but nevertheless fairly conventional spherical supernova explosions. However, astronomers have now found that these stars may well have blown apart in a more powerful asymmetric fashion, spewing forth jets violent enough to eject heavy elements into neighbouring galaxies. These elements ultimately served as seeds for the next generation of stars, some of which can still be observed today. And this is where our story begins. A report in the Astrophysical Journal and on the prepress physics website archive.org has found a strong abundance of the element zinc in an ancient second-generation star known as HE1327-2326. The authors believe the star could only have acquired such a large amount of zinc after an asymmetric supernova explosion of one of the very first stars that had enriched the molecular gas and dust cloud from which it was eventually born. One of the study's authors, Professor Anna Freebell from MIT, the Massachusetts Institute of Technology, says when one of these massive stars explodes, they collapse to form a black hole. And while a lot of the progenitor star will get sucked into the black hole like a vacuum cleaner, some of the material escapes before it reaches the event horizon, that point of no return. And that material is being shot out as a jet, which, having escaped the black hole, can be observed later. And Freebell believes that's exactly what's happened with HE 1327-2326. If correct, this is the first observational evidence of such an asymmetric supernova taking place in the early universe. And it changes science's understanding of how the first stars exploded. HE 1327-2326 was discovered by Freebell back in 2005. At the time, the star was the most metal-poor star ever observed, meaning it had extremely low concentrations of elements heavier than hydrogen and helium, the elements created in the Big Bang. That's an indication that it was formed as part of the second generation of stars, at a time when most of the universe's heavy element content had yet to be created. That's because other than hydrogen and helium and a little bit of lithium, which were created in the Big Bang, all the other heavy elements in the universe were created in stars, either during their lifetimes or when they died. While the very first generation of stars were so massive they exploded almost immediately, relatively speaking, some of the smaller stars, which formed as the second generation, are still around today, and they preserve the early material left behind from those first stars. And HE 1327-2326 is a good example of that, with just a sprinkling of elements heavier than hydrogen and helium in its makeup. So astronomers knew it must have formed as part of that second generation of stars. The other good thing about the star is that it orbits close to the Earth, just 5,000 light-years away. And in May 2016, the authors were given the chance to observe the star in detail using NASA's Hubble Space Telescope over a 2-week period. They recorded the starlight over multiple orbits and took spectroscopic readings of the star to determine its composition. Now, the spectrograph on Hubble is designed with high precision to pick up faint ultraviolet light. And some of those ultraviolet wavelengths are absorbed by certain elements such as zinc. The researchers made a list of heavy elements that they suspected might be within such an ancient star. They then planned to look in the ultraviolet data for these elements, including silicon, iron, phosphorus, and zinc, and they found a very strong zinc line. The next problem was determining how such an ancient star wound up with such a really strong abundance of zinc. In order to determine how this ancient star wound up with such a really strong abundance of zinc, the authors used computer simulations of supernovae and the secondary stars that form in their aftermath. They ran over 10,000 simulations of supernovae, each with different explosion energies, configurations, and other parameters. They found that while most of the spherical supernova simulations were able to produce a secondary star with the elemental compositions the researchers observed in their target star, none of them were able to reproduce the strong zinc signal. The only simulation that could explain the star's unusual zinc makeup was one involving an aspherical jet-ejecting supernovae of a first-generation star. Such a supernova would have been extremely explosive, with a power equivalent to about 1 nonillion times that of a hydrogen bomb. And before you look it up, 1 nonillion is a real word. That's a 10 with 30 zeros after it. The findings are important because they mean supernovae produced by the death of the universe's very first stars were 5 to 10 times more energetic than previously thought. And the findings will also force scientists to change their understanding of reionization, a pivotal period in the universe's evolution during which the neutral hydrogen gas which made up most of the universe was morphed from being completely neutral to being ionized, a state that made it possible for galaxies to take shape. These first supernovae would also have been powerful enough to shoot heavy elements into neighbouring virgin galaxies, that is, galaxies that had yet to form any stars of their own. Freebell says once you have some heavy elements in a hydrogen and helium gas, you have a much easier time forming stars, especially little ones. She says her working hypothesis now is that maybe second-generation stars of this kind formed in these polluted virgin systems, and not in the same system as the supernova explosion itself, which is what people had always assumed. Now, if correct, this opens up a brand new channel for early star formation. I'm Stuart Gary. You're listening to SpaceTime. New Zealand's Rocket Lab has successfully launched another Electron rocket, placing 3 satellites into orbit for the US Air Force. The launch from the North Island's Mahia Peninsula was the second this year for the company, coming just 5 weeks after the company's last flight.
Stage 1 confirms stage 1 is pressed.
Stage 1 pressed.
Stage 2 confirms stage 2 is pressed.
Stage 2 is pressed. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
Stage 1 propulsion propulsion is nominal.
We've had successful liftoff of Rocket Lab's STP-27RD mission on That's a Funny Looking Cactus. The next major milestone we're coming up to is Max Q, or maximum aerodynamic pressure.
Guidance is nominal.
This is where the forces on the vehicle are at their greatest during flight.
Coming up on Max Q.
And there you have it. Electron has passed through Max Q, or maximum aerodynamic pressure.
Stage 1 propulsion is nominal.
Coming up soon, Electron will go through a series of key mission milestones in relatively quick succession. Starting with main engine cutoff, or MECO, the 9 Rutherford engines on Electron's first stage will shut down in preparation for Stage 2 separation. Following this separation, we'll see ignition of the vacuum-optimized Rutherford engine on Electron's second stage.
Speed is 2 kilometers per second.
Entry burnout detect mode.
Stage 1 MECO.
Stage separation succeeded.
Stage 2 engine started.
We have had MECO, or main engine cutoff. Electron's first and second stages have separated from each other, and the vacuum-optimized Rutherford engine on Electron's second stage will continue onto orbit.
The Electron's kick stage deployed its 3 satellite payloads into their designated orbits 54 minutes after launch. The STP-27RD mission for the United States Department of Defense test program was Rocket Lab's heaviest payload so far, with an all-up mass of around 180 kilograms. Included in the payload was a space plug-and-play architecture research CubeSat-1, which was sponsored by the US Air Force Research Laboratory Space Vehicles Directorate as part of a joint American-Swedish experiment studying new avionics miniaturization technologies for radio and space situational awareness systems. Another payload was the United States Air Force Academy Falcon Orbital Debris Experiment, which is designed to evaluate ground-based space junk tracking systems. The third satellite in the payload was the York Space Systems S-Class satellite for the United States Army. It's designed to demonstrate how a small experimental commercial satellite could meet their space capability requirements. Rocket Lab's busy manifest will see launches every month for the rest of the year, with that scaling up to flights every 2 weeks by year's end. That busy schedule will be helped with the opening of a second launch pad later this year at NASA's Wallops Island Flight Facility on the Virginian mid-Atlantic coast. And time now to take a brief look at some of the other stories making news in science this week with the Science Report. A new report confirms there can now be no doubt that planet Earth has entered its 6th mass extinction event, and this one is being caused by humans. The latest assessment of global biodiversity by the Intergovernmental Science Policy Platform on Biodiversity and Ecosystem Services paints a gloomy picture of the accelerating decline of life on Earth. Habitat loss, climate change, pollution and invasive species are singled out as the primary drivers of the decline, with around 1 million species already facing extinction. The 1,500-page report on the state of biodiversity on Earth was compiled by a team of 145 scientists from 50 countries and sums up some 15,000 scientific peer-reviewed papers on the threats against life in the age of humans. The report warns immediate action needs to be taken to reduce the intensity of drivers of biodiversity loss. Scientists found that human activity is destroying the very ecosystems we depend on for food, water, and natural resources. The United Nations-backed report is the first single unified statement from the world's governments that unambiguously makes clear the crisis we are now facing for life on Earth. It finds that species of all kinds, mammals, birds, amphibians, insects, plants, lizards, marine life, terrestrial life, are all disappearing at rates tens to hundreds of times higher than the average over the last 10 million years. And the bottom line is, it's all due to human activity. A new study says global alcohol consumption is set to increase from 5.9 litres of pure alcohol per year per adult in 1990 to 7.6 litres by 2030. The findings, reported in the Lancet Medical Journal, means the world is not on track to achieve any sort of global alcohol reduction. Scientists found that most alcohol was being consumed in high-income countries, with Australia, a good example, still almost double the global average at just over 2 standard drinks a day per adult. That's despite decreasing levels since 1990. In Australia, alcohol consumption dropped from an average of 12.9 litres per adult in 1990 to 10.7 litres per adult in 2017, and it's predicted to remain fairly stable at that rate until 2030. The report predicts the global increase to 2030 is likely to be driven primarily by low- and middle-income countries. Paleontologists have uncovered a fossilized dinosaur with bat-like membrane wings in addition to feathers. The 163-million-year-old fossil suggests there was a lot of experimentation with wing structures going on when flight first evolved. The fossil, which was uncovered at a dig in China, is the second of this type of dinosaur to have these wings, which were previously only known from pterosaurs. You can read more about the study and the findings in the journal Nature. Now, sticking with reptilian paleontology and reconstruction of the most complete fossil lizard ever found in Australia, a 15-million-year-old relative of the modern-day blue tongues and social skinks family, reveals the ancient creature was equipped with a robust crushing jaw and was remarkably similar to modern-day lizards. The new study, led by Flinders University and reported in the Journal of Vertebrate Paleontology, combined the anatomy of living fossils with DNA data to put a timescale on the family tree of Australia's social skinks. The fossils from the Riversley World Heritage fossil deposits in northwest Queensland came from a creature that looked something in between a tree skink and a blue-tongue lizard. It would have been about 25 centimetres long, and unlike any of the living species, it was equipped with robust crushing jaws. The results show that Australia's blue-tongue lizards likely split from this creature as early as 25 million years ago. Well, while we and the rest of the world joke about it, apparently it's true. A new study has found that more than half of British men and women aged between 16 and 44 have sex less than once a week. The findings, reported in the British Medical Journal, shows a general decline in sexual activity in Britain between 2001 and 2012. The study used data from more than 34,000 people to measure changes in actual and preferred frequency of sex, and to examine factors associated with sexual activity. It found the steepest declines are among the over 25s and those who are married or living together. You're listening to Space Time. I'm Stuart Gary, and that's the show for now. You can subscribe and download Space Time as a free twice-weekly podcast through Apple Podcast iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, from spacetimewithstuartgary.com, or from your favourite podcast download provider. Spacetime's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C., and available around the world on TuneIn Radio. If you want more Spacetime, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us on Twitter through @StuartGary, at Spacetime with Stuart Gary on Instagram, and on Facebook, just go to www.facebook.com/Spacetime with Stuart Gary. Spacetime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to Spacetime with Stuart Gary. This has been another quality podcast production from Bytes.com.